Hey guys, hello everyone. Welcome to Rasayan Academy, all of you. So it's been a while since I've uploaded a video, and now we are going to continue the discussion with the addition reaction to alkenes because we have talked about the substitution reactions, elimination reaction. The next important type of reaction in the reaction mechanism series is addition to alkenes and many other functionalization reactions on alkenes, right? So, yeah, here we are going to continue the discussion and let's talk about some really important reaction. Now, first of all, we would like to discuss about how many types of addition reaction that we usually see. So, we have two types of unsaturated bonds. The one which is formed in between a carbon and a carbon, just like this one, and this one as well. And the other type is where you are having a heteroatom that may be a carbonyl, that may be, let's say, an imine or a thiocarbonyl, and so on and so forth. And then we have a triple bond as well. So these are all the bonds where we usually see unsaturation, right? Now, what are the types of reaction of all of these? Let's look at them one by one. First thing, we usually add to this simple alkene, we usually add HBr, which is going to be added in this way, one hydrogen over here and the Br over here. This is known as hydrobromo addition or basically electrophilic addition. Why is that so? We'll talk about that as well. So we have added one molecule having two different atoms. Then we can add one molecule with the same type of atoms. We can use dichloro or dibromo addition. Similarly to the carbonyl bond or to any other heteroatomic multiple bond, we can add two different atoms like this, a hydrogen H plus as well as a Cn minus. So this is going to be a little bit of a different mechanism because the cyanide attacks and then the proton is grabbed. However, this is a different mechanism. A proton is grabbed first and then the bromide attacks. So there is a little bit of a difference in these. We are going to talk about it. And yes, the last one, there is a triple bond over here. So how does the triple bond add? What does it give you as a product? It doesn't look like as if you're going to get this product because usually you're going to add the OH, let's say, to the central bond and the proton to this bond, to the this carbon. And why this selectivity, why not the other selectivity, all of those things we are going to talk about in detail. This is going to tautomerize to give you this molecule. All right, so many different types of addition reactions are possible. Let's talk about them one by one. Now, first thing, mechanism of electrophilic addition reaction. So today our focus is going to be mostly on the addition reaction to alkenes, right? So let's see. Alkene is electron rich, as you already know. Why is it electron rich? Because it is having a pi electron cloud surrounding both of these carbons, right? And that is why it is most likely to invite an electrophile. What is an electrophile? Anybody with a positive charge or with an octet not complete. Let's say BH3 is also an electrophile. Anybody which can behave as a Lewis acid can also behave as an electrophile. That's the thing, right? And then the electrophile is attacked. You are going to first get a slow step because the pi electron density is disrupted and you get a positive charge on any one of these carbons. After that, in the next step, the negative charge, or let's say the lone pair, whichever it is, an electron rich molecule or a nucleophile is going to attack. So you might ask this question that both the electrophile and the nucleophile are getting added, then why particularly electrophilic addition? Because first the electrophile adds. Whichever species adds first will be deciding the name for that reaction. Alright, so similarly for a carbonyl, because the electron density is low on the carbon, a nucleophile is invited over here, and that's why we call it nucleophilic addition. Alright, now guys, the most important part of doing all of these reactions is understanding stereochemistry as well as the regioselectivity. So we are going to talk about both of these one by one, but first thing we talk about is stereo, because there is no reaction mechanism without stereo. Now first thing, we have to understand what kind of addition is this. Is it a syn addition or an anti addition? See, if the addition is syn, the product is going to be erythro-DL pair if you are using a cis alkene. Now this may sound like really big terms, but let me tell you, syn addition is nothing but adding two of these groups Y and W, or X and Y, whatever it is, adding both of these group on the same side of the double bond. Actually, I would not say same side, I should say same face. Why? Same face of the alkene. Why? Because it matters a lot when you talk about stereochemistry. An alkene has two faces, right? Because if we draw the alkene like this, let's say, the same alkene, if we draw like this, you will understand that there is a top face and then there is a bottom face, right? So syn addition is when you're adding X and Y, or let's say these two group Y and W on the same side or on the same face of the alkene, let's say from the top. All right, or let's say from the bottom but from the same side. Okay, so if we have taken a cis alkene, for example, both the A groups are on the same side. This is our cis alkene. All right, yeah, let's talk about this cis alkene. So both the A are on the same side. Now if we are adding Y and W, this, all right, then it is going to be like this. Both of them have added in the same way. So how do you draw this molecule in the Fischer projection? You are going to draw this molecule in this way. This is A and B, A and B again, Y and W are like this. So this kind of a molecule is known as an erythro molecule, where there are only two groups on this vertical line and the other groups are on the same side. The same groups are on the same side. This is erythro molecule. Similarly, if let's say we have changed the regioselectivity, we have put our W over here and Y over here, but the A is on the same side and we are adding from the same face, that is going to give you another possibility. Now if you draw the Fischer projection for this molecule, it's going to look like this again. But here W is above. And what is the relationship between these two molecules? These are just the, mirror images of each other. And that's why it is said you are getting a DL pair. That is isomers, racemic mixture you are getting. Because each carbon has a 50% chance of being attacked by Y. Alright. So till now we have not yet decided the regioselectivity. So that's why we say that each carbon is having 50% chance of being attacked. And the syn addition on an erythro molecule, or let me just give you a very, so for example, I will be giving you an example over here. Let me erase each and everything. Let's consider this once again, because the stereochemistry is the most important thing. Right. So now I am adding H2. Let's say I'm adding hydrogen. And in the presence of platinum charcoal, you know that this is catalytic hydrogenation of an alkene. So both the hydrogens are going to add on the same side. Then what would you get? You would get a molecule like this, that both the hydrogens are here in this way, A, B, A, B. So if you write this in the Fischer projection, you get hydrogen, hydrogen, A, B, B, like this. So this is no more erythro. This has become meso. The molecule has become meso. This is no more an erythro DL pair. So we have to modify one more thing in our, then it is going to be like short trick to understand this and to remember this, that if you are doing syn addition, if you are doing syn addition on a cis alkene, that is going to give you the erythro molecule. If you are doing syn addition on a trans alkene, that is going to give you trio DL pair. Similarly, if you are doing anti addition on a cis alkene, then you are going to get the trio. And if you do anti addition on the trans, you're going to get erythro. You can try this out by trying the same reaction on different molecules. A shortcut cis alkene anti-addition should give you 3O. There is a big thing you need to know, that if you are adding, let's say, same kind of molecule, shortcut, that is on a cis alkene, if you are taking any molecule which are having like same groups like hydrogen or anything like that. So on a cis alkene, if you are doing syn addition, either you will get erythro depending on the molecule. Let's say you are taking HX, you will get erythro. If you are taking H2, you are going to get a meso molecule. Similarly, on the trans, if you are getting syn, if you are doing syn addition, you will always get 3O and you will always get an active molecule. Even if you are taking hydrogen, then also you will get an active molecule because the groups are trans over here. Similarly, if you do cis alkene addition but you are doing anti-addition, even if you take hydrogen, then also it will be 3O and active. Alright, because the addition is anti. Alright, always it is going to be active. But if on a trans addition, if you are doing trans addition, trans molecule, if you are doing anti addition, and if the groups are same groups, for example 2 OH groups, you are getting, let's say, dihydroxylation, right? You will get a meso molecule. So be careful about what kind of molecule you have taken. This slide is completely for shortcut. Cis alkene syn addition gives you erythro or meso. Trans alkene syn addition 3O and active always. Cis alkene anti-addition always active in 3O. Trans alkene anti-addition erythro, or it may be meso. So whenever there is an erythro, there is a possibility of meso depending on the group that you are taking. Very easy shortcut. Let's all right. For example, we are doing anti-addition on a cis alkene again. So what should we get? Let's see. Yes, we have 3O. So this shortcut hence proved is very important. So we are, again, our alkene is planar like this. All right, these I've just tried to write this perpendicular to the plane of paper so that we understand that we can attack from one phase and from another phase. So one of the atom is attacking from one phase and the other atom is attacking from the bottom phase. That gives you this kind of a molecule. Now this is written in the staggered format. All right, all you have to do is you have to first take it into the eclipsed form so that you can write a proper Fisher projection. All right, let's say I have rotated this by 180 degrees. When I do so, this is Y and the A is going to be up here and the B is up here. So how do you write this in the Fisher projection? You have to imagine it from the top. You are going to get a Fisher projection in this way, right? This is this carbon up front. This is what you are getting. So what kind of a molecule is this? W and Y are on the vertical line. The same groups are present on the opposite side. So this is a 3O molecule. All right, and that depends on what groups you are adding. Let's say if you are adding different groups, you are going to get erythro and 3O DL pair in both the cases. All right, but onwards now. So yes, we have proved what we had to. Now let's move onwards and see a real example. Now here it is. We have got Z butene and E butene. All right. So yeah, what are we going to do with these? Let's say we are doing bromine addition. Now bromine addition, you have to know, is anti-addition reaction. What does bromine do? Bromine, usually, let's say we draw the alkene like this once again, that is one of the groups above and the other two below. So the bromine adds in this way. First of all, there's going to be Br2. The alkene attacks over bromine. These two groups are above. One bromine is on the plane of paper. Another two groups are below like this, and a bromonium ion forms. Now the other Br minus is going to attack either over here or over this carbon. That's going to give you similar possibility and similar product. So This is how you get anti-addition. This is the product of anti-addition. Now you see the same thing has happened over here. You have got one bromine over here and the other over here. Similarly, there is an inversion on this particular carbon. This particular carbon, there is inversion like this. Now, once again, we see the conclusion that we have got from our shortcut, that Z-alkene or cis-alkene, if we are doing anti-addition, what do we get? We get a DL pair, a trio molecule and a DL pair, right? Even if the groups are same, because they are anti, we are going to get a DL pair and trio. Similarly, we have a transalkene and we are trying out anti-addition over here. The groups are same as well. So what do we suspect? We suspect that we are going to get a meso molecule, and that is exactly what we get. So our shortcut is useful, isn't it? Try to slowly stop the video and try to understand what I'm trying to say, try to apply the knowledge. This is going to be really helpful. Now here comes the regioselectivity. See, regioselectivity is equally important because not always do we get symmetric alkenes. Many a times we are going to get unsymmetric alkenes, right? So look at this compound. This is an unsymmetric alkene. There are two methyl groups on this carbon and two hydrogens over here. So when we are taking bromine and we are doing anti-addition of bromine, since two of the groups are same, that's why you end up getting the same product. So you open from wherever you want, you're going to get the same product, whichever end is attacked. That's not a problem. But the problem arises when we are having a difference in reagent as well as a difference in the substrate. So an unsymmetric alkene is going to form the bromonium ion in the same way, just like this one. But if we are having any alcohol like methanol, this is always going to attack the more substituted end of the bromonium ion. This is to our surprise, because we might think that okay, this is the bulky end and isko yahan attack karna chahiye because it is less hindered, and it should attack over here so that easily this bromide opens. But no, that does not happen. Very important. To an unsymmetric alkene, the methanol through the bromonium ion is always going to attack on the more substituted end. Why does it happen? Is it going through the SN1 mechanism so that we get a more stable carbocation like this? This is a more stable carbocation, isn't it? But yeah, if you are doing SN1 reaction, you also have to keep in mind that this methanol can attack from above the plane as well as from below the plane. So there must be a mixture of stereoisomers that you are getting, isn't it? But no, that's not the case even. You are not going, this molecule is not completely going through an SN1 mechanism either. What do we call it? We call it loose SN2. We call it loose SN2 mechanism. There's a reason for this, because neither it is a complete SN1 reaction and nor it is completely SN2. Because if it was SN2, we would explain this through the less hindered side attack, and if it was SN1, we would explain it through a more substituted carbon attack. लेकिन ये दोनों ही नहीं है, because there is inversion in stereochemistry, right? And there is the attack on the more hindered carbon. So methanol attacks over this carbon in such a way that the bromonium ion is only like kind of stabilizing a carbocation, right? It is a loose SN2 reaction. There is always going to be this backside attack like this, and you finally follow the mechanism like this. This is your major product. How important it is, because this is just opposite to what we would think about it, right? Very important. Regioselective addition of bromine to an alkene. Now guys, there is one very important thing that we want to discuss about addition of some molecules. Let's say it was very clear to us that bromine addition is anti-addition. Stereochemically it is anti-addition. But how do you add HBr and how do you add water? Are they also anti-addition or are they syn addition? This is confusing and it is not mentioned in most of the books. Now, the thing is, guys, they always don't follow the same mechanism. Read out the following paragraph. Right, the addition of HX is varied. Examples are known of predominant syn, anti, and non stereoselective addition. It was found that the treatment of 1,2-dimethylcyclohexene, this one, with HBr gave predominant anti addition. Alright, so when we are reacting HBr, we have a hydrogen added below and we have the the bromine added above. It may be possibly going through the hydronium ion formation, maybe. Is it possible? It is not seen in, it is not predicted in many of the reactions, right? Because hydrogen is very small to be able to coordinate with these two carbons at once. So the idea of forming a hydronium ion is not good. But this is shown to be anti-addition, and the addition of water to the same gave you mostly equal amounts of cis and trans alcohol, like as if there was a carbocation formation taking place, and that's why it is going to add from both the side, and that is so. This mechanism goes through a carbocation formation. All right. On the other hand, the addition of DBr to this particular compound and to indene gave predominant syn addition. So all of these compounds, it gave you syn addition of DBr. All right. So there is no bromonium ion or deuteronium ion, whatever it is called. It is not even forming. This give you syn addition. So can we predict these kind of stereochemistry? Not always, we cannot predict, right? It may be sometimes, like in the case of water, we know that it's going to go through a more stable carbocation because water is a very polar solvent. So we know it's going to form a mixture, but we cannot predict for all the molecules, right? Okay, now let's move onwards to another important discussion, that is addition to conjugated systems. Now there are dienes which are reacting regioselectively with the electrophiles, and we have to be careful what product we are predicting. For example, this is a diene molecule, right? There are two ways the Y and W molecule can add to it. The Y could be added on this particular carbon and the W also added on the adjacent carbon. This we call as 1,2 addition or direct addition product. Similarly, Y is added on this carbon and the W is added on the fourth carbon. So we call it 1,4 addition product or conjugate addition product, right? So if you have studied the thermodynamic and kinetic control, you will know that the 1,2 addition product is known as the kinetic product because the formation requires less activation energy, but the more stable product is 1,4 product. So this is known as the thermodynamic product, which is more stable, although it requires high activation energy, but the stability of product is higher. Why? Because you have a more substituted alkene as compared to this one. All right. Right, now we move onwards and we always see that depending on different kinds of molecule we are going to have different possibilities. So let's say butadiene molecule gave only 20 to 25% of 1,4 adduct at low temperatures, while at higher temperatures, where attainment of equilibrium is more likely, the mixture contains 75% of 1,4 product. So let's look at the butadiene system. It's like this. So let's say if we are adding HBr to it, for example. Now the HBr, usually first of all the alkene is going to attack over the H plus. This is how the conjugate addition works. So this is 8 hydrogen added over here, you're getting a positive charge. Now on low temperature, at low temperature where a very high activation energy cannot be provided, so at this point you are absolutely going to get the HBr addition right over here. But when the reaction has more time, when you are getting more time, and more heat, then absolutely you are going to form this product, which is the thermodynamic product, the 1,4 product. And that is what is given in the this example. 20 to 25% of 1,4 addition product only at at lower temperature, and when the temperature is increased it becomes 75% because you have enough heat and energy, right? So another great topic of our interest is formation and reaction of epoxides. So we need to understand how the epoxides are forming, and more than that we need to see what is the regioselective ring opening of the epoxide. These are very very important examples that we are going to discuss today. So formation of epoxide on an alkene. So guys, you know that the alkene is electron rich. It has been inviting electrophiles. So if you want to add an oxygen, we want to add an oxygen which is delta positive. But how is that positive possible? Oxygen is electronegative. ये delta positive कैसे होगा guys? So the commonest oxidant is a per acid या per oxy carboxylic acid. इसके पास इतने oxygens होते हैं that any one of these is going to be positive. How? Let's see. So this oxygen can give electron density into the carbonyl, right? And while it does resonance, it is going to take electron density from this particular oxygen. So it becomes electron deficient, it becomes delta positive, and this is the one which is going to be transferred to this alkene. So how does the reaction proceed? It attacks over here, the bond leaves. This oxygen is going to attack back, and the hydrogen is taken away by this oxygen, such that this process you must have seen is a concerted process. Alright, that is epoxidation by the per acid is already always concerted, and it is going to give you the simple carboxylic acid as the remainder. Alright, and we have here used metachloroperbenzoic acid, which is the most common epoxidizing agent. Now guys, what is the stereochemistry? As I said, it is going to be a concerted mechanism. So if you are using a cis alkene, it is always going to give you a cis oxide. If you use a trans alkene like this, it is always going to give you a trans epoxide. Trans epoxide formation will only take place when the alkene is actually aliphatic. If you, let's say, have some kind of trans double bond which is in junction of two rings, then it is not possible to get it, right? I just hope you get my point. It's very simple. Trans alkene has to be aliphatic, like non-cyclic. Okay, next very very important point is how do we compare the reactivity of alkenes, right? So look at this. With metachloroperbenzoic acid, you have seen the structure and you know that this oxygen is delta positive over here. So to this particular reaction, to this particular reagent, how electron rich our alkene has to be to react. You see the scale over here. As the substituents, as the methyl substituent go on adding on the alkene, the reactivity goes on increasing, and the maximum is for tetra substituted because it is the most electron rich. That is why epoxidation is very easy over here. Now we move onwards and we also see one more important reaction, that is formation of epoxide. We have seen through metachloroperbenzoic acid, through any other per acid, it will give you the same mechanism, concerted. But here we need to see the more important reaction, that is regioselective opening of the epoxide, and that depends on conditions. What condition? On acidic condition as well as basic condition. It will give you two regioisomers. Very, very important over here. That is the reaction of epoxide acidic methanol के presence में, it is always going to open the ring. See, methanol is always going to attack over the more substituted carbon. It is just like what we did for the unsymmetrical bromonium ion. When the bromine and methanol was present, in the presence of acidic condition, it's always going to give you like a loose SN2 mechanism I told you. See, methanol and acid, it is doing the same thing, right? Just like the bromonium ion, the methanol is going to attack on the more substituted carbon. lose SN to transition state, and it gives you this kind of a molecule. This is the regioselectivity. In the presence of acid, methanol attacks on the more substituted carbon. But when we are taking the base, when we have taken the base over here, you see that the methanol has become a methoxide, and now it has become a more powerful nucleophile. So it does not have enough patience to check for the more substituted carbon to give the more stable product. No, it's just directly going to attack over the less hindered side and open up the bond. So the methoxide is a more powerful nucleophile and opens the ring from the less substituted carbon. Right? This is most important. In the presence of a base, the attack is from the less hindered side, right? And in the presence of an acid, the attack is from the more hindered side. All right? Now you know the reasons of both of these. So, yeah, this is what we have in the basic medium. The methoxide is attacking on the less hindered side, giving you SN2 like transition state, and this is your final product. Now, as promised, I have taken examples from different books from Jerry March, from Claydon, everywhere. These are from Caruthers, right? So you see, there is a selectivity in epoxidation over here. This is our example number 1 of chemoselectivity of these two alkenes, basically. That is, which alkene will react? Definitely with metachloroperbenzoic acid, the alkene which is more electron rich will react and will give you syn epoxide. Alright, epoxide from the same side. Secondly, in this compound, in the second example, you see there are two alkenes over here. One is trans and the last one is a terminal alkene. Which one will epoxidize? The one which is more electron rich. Definitely this one. And the stereochemistry is as it is reproduced. You get a trans alkene, you get a trans epoxide. This one kept untouched. Alright, this is the selectivity. Moving onwards, third example, and this also talks about a directed epoxidation. How are we getting a directed epoxidation over here? And what does that mean? Directed epoxidation means that in the presence of any group, the metachloroperbenzoic acid is going to be directed to give the epoxidation on same side. Look over here, this particular example. It is an allylic alcohol, and not just allylic alcohol. If the OH was on this carbon, then also the metachloroperbenzoic acid will give you same side epoxidation. So we say for the homoallylic as well as allylic, the directed epoxidation works for both. So you see here in the first example where there is a bulky group present on the allylic position, you are getting only 40% of the epoxidation on the same side of this ester group and 60% on the opposite side. This is majorly driven by the steric reasons, steric hindrance. However, when there is an OH present, 92% on the same side and only 8% on the opposite side. Why is that so? Because this OH group is actually doing hydrogen bonding. It is doing hydrogen bonding with the proton of the metachloroperbenzoic acid like this. This oxygen has to be transferred in this way. Alright, but the oxygen is doing hydrogen bonding, so it is because of hydrogen bonding you can answer that the metachloroperbenzoic acid is doing a directed epoxidation. Now the last example is with a different reagent. This is DMDO. What is DMDO, guys? What is DMDO? It is basically DMDO is basically dimethyl dioxirane. So you have dimethyl dioxirane, something like this. So the DMDO molecule is dimethyl dioxirane. It's going to look like this. And it is made by the oxidation of a ketone from peroxomonosulfate. Alright. And this also works similar to metachloroperbenzoic acid in providing this oxygen, alright, to a double bond. Now, the same work that is done by metachloroperbenzoic acid can also be done by DMDO. And here you see that it is going to, in this particular example, it is going to transfer the oxygen below the plane because there are these two bulky groups, benzylic ether groups present above. So the epoxidation takes place below on the alpha phase, and that gives the major product. Lastly, guys, I also wanted to pinpoint the very, very important asymmetric epoxidation reaction. Now, if you have already seen my name reaction, that is the Sharpless Epoxidation, it's going to be really easy for you to understand this. If you have not, please go and see Sharpless Epoxidation reaction. Very, very important it is. So, the reactivity, there are only two reactions, only two type of reactions possible under Sharpless epoxidation, that is, if you have got an allylic alcohol just like this one, either you are going to get the epoxidation below or you're going to get the epoxidation above. When do you get the epoxidation below? See, you have, I don't say above or below, I say that in this condition, and I find out re and psi phase first of all, and then based on that I say whether the epoxidation is going to be above or below. So yeah, this example you can cover from Sharpless epoxidation because it is exactly the same thing discussed over there as well, that also in much detail, right? So yes everyone, I will see you all in another such video very, very soon. And keep on studying, keep on practicing, guys. Reaction mechanism is a wide part of organic chemistry, and I hope that I'm helping you cover it. Thank you so much for watching. I'll see you soon.